Okay, so today we're going to talk about something called piecewise functions, but before we get into piecewise functions, we're going to start off with functions that have restricted domains. So notice the instructions say graph each function and identify the range. Generally, when you've graphed functions in the past, there hasn't been a restriction on the domain, so it's like you could plug in any number you wanted and then graph the shape of that function. But now we're going to have rules for what we can plug in for our x value or our domain. Now, for each of these functions, remember what you've learned about parent functions. So the key is you need to think about generally what the shape of that function is going to be so that you know how many points to plot and which points to plot so that you get the correct shape of the graph. So for our first example, notice we've got f of x equals x plus 2. Hopefully at this point you're comfortable saying automatically that this is going to look like a line. With lines, you only need to plot 2 points. Remember, from geometry, through any 2 points there is exactly one line. So don't waste your time plugging in more than 2 points. Just 2 points are fine. And in this case, because we have a restriction on the domain, the 2 points you need to plug in correspond with the endpoints of the domain. So instead of just going straight to the table, I'm going to kind of show you the concept of these restricted domain functions. So let's for a second graph f of x equals x plus 2 as though there was no restriction on the domain. So notice our y-intercept is 2 and our slope is 1. So I'm going to plot the y-intercept first, and then I can go up 1 and over 1. I'll plot a couple more points just to make sure my line is nice and exact. Now, this is what that function would look like if there wasn't a restricted domain. We need to look at the part of the graph that corresponds with that restricted domain of -5 is less than x, which is less than or equal to 3. So I've created these boxes where we can highlight the area of the coordinate plane that we need to look at. So notice we're going from -5 to -3. In other words, for this function, we only care about, or we can only graph, or another way to say it is, the function is only defined for anything in that section. Okay, so now we don't care about any part of the line except for what's in that pink box. So we're looking right here. The next thing you need to look at are the endpoints. If you recognize our inequality, -5 is not included. So remember from your experience graphing inequalities, to show that a number is not included, we're going to use an open circle or an open dot. -3, however, is included. So we can go here to -3 and have a closed dot. Now what we can do is we can look at the range. Remember, the domain is showing the lowest to the highest x value included on that function, and then the range is going to be showing the lowest and highest y value, or another way of saying it is all of the possible y values. So if I were to draw another box that encompasses the highest and lowest points on that graph, notice over here it goes from -3 to -1. Notice because -3 has an open circle associated with it, the 3 is not included as a part of the range. So if we were just to write the range in set builder notation, we've got y, it needs to be greater than 3, or -3, excuse me, and less than or equal to -1. If we wanted to do that in interval notation, our lowest number is -3, our highest number is -1. -3 is not included, so we need parentheses. -1 is included, so we need a bracket. Now, if you were to graph that just by plugging points into a t-chart and plotting points from there, we would plug in a -5 for x and get a -3. Notice what I'm doing here. I'm not going to show the work on all of this, but I would plug in a -5 for our x and then add 2 to get -3, and then a -3 for our x and add 2 to get a -1. And notice that also corresponds with our range value. Okay, so let's go on to the next one. So first thing, let's keep in mind what our parent function would look like. If you've got an x squared as your highest degree term, you know that this is going to be a parabola. So it's going to look something like that. Now notice our domain is restricted to x can only be less than or equal to 0. Now because this has a curve, I would recommend at least plugging in 3 points. So if we plug in a 0 for x squared, so we'll have 0 squared, which is equal to 0. Be really careful. It's super common for students to plug in a -1 squared and say that the solution or the answer there is -1, but it needs to be you need to make sure that you include the negative as a part of the base. So then -1 squared is +1, and -2 squared is +4. So again, I'm going to use a colored box to identify the area that we're looking in. So x is less than or equal to 0. So we're going to only be looking in the portion of the graph that's in the pink box. Now remember, if it's a parabola, and notice this is the parent function. So if I were to sketch it loosely, it would look like this. But because of our domain restriction, the function is not defined for anything outside the pink box. Now let's get some exact points though. So we're going to plot the point 0, 0 from that first line. Then we'll plot the point here, -1, +1, and -2, +4. And now we can connect our dots with a curve. We've got a really accurate picture of this restricted domain function. So I want you to notice that even though I've shown the domain with a box, this domain would keep going on forever to the left, and the range will do the same thing. So if we were to show the lowest and highest value for the range, there really isn't a highest value because that box would keep going and getting higher and higher and higher and higher. So for our range, we're going to say that the y is anything greater than or equal to 0. Why is it equal to? Because that 0 is included in the domain, so it's also going to be included in the range here. So if we were to write that instead in interval notation, our lowest number is 0, keeps going forever to positive infinity. 0 is included, so we need a bracket. Infinity can't be included, so we always need a parentheses. All right, let's go on to example 3. So first, make sure you pay attention to what kind of function you're dealing with. This is going to be a square root function. So remember, the general shape of a square root function is this. So you need at least 3 points to make sure that you have a good shape. So I'm going to go ahead and highlight the area of our graph that we're going to be looking in. So we're going from -3 to 0. So we're going to be plotting points within that pink box, or in other words, the function is defined for values only within that pink box. So again, make sure you include, in the numbers you plug in, include any numbers that are associated with the restricted domain. So if I plug in a -3, if I do -3 plus 4, that's a 1, square root of 1 is 1. -2 plus 4, that's the square root of 2, which is about 1.4. And then 0 plus 4, the square root of 0 plus 4, which is the square root of 4, which is 2. So now I can go in and I can plot those points. So -3, 1. -2, 1.4, which is going to be right here, and then 0, 2. And notice it pretty closely follows the shape of that general parent function. So there's our shape. Now we've got to pay attention to our endpoints. Notice we've got less than signs associated with both. That means that -3 is not included as in the domain, so we have an open circle there, and 0 is also not included in the domain, so we have an open circle there. So now if we were to look at our range, we're looking for the lowest and the highest point on the graph. So here, I'm going to draw a box. And notice the y values associated with that. You can see them here. There's a there's a 1 and a 2, or you can also see them here, a 1 and a 2. So keep in mind, because your circles are open, or in other words, -3 and 0 are not included as in the domain, then 1 and 2 are also not included in your range. So we need to use a less than sign, or if you're writing an interval notation, you need parentheses. So those are not piecewise functions. Those are just one function graphed over a restricted domain. Now we're going to get into actual piecewise functions. So first, let's do a definition. A piecewise function is a function that's built by pieces of different functions over different intervals. So it's basically like doing what we've done already, but there's going to be more than one function on one graph. So here, let's look at example 4. First, keep in mind what the parent functions look like. So this is an absolute value function, so we need to make sure that when we graph it, we have a portion of a v. And then for the second function, or the second part of this piecewise function, we have a square root, so we need to make sure we have a portion of that curve. All right, so let's go ahead. We're going to plug in points. Because neither of these are just straight up linear, you need to probably plug in at least 3 points, but be really careful, especially on the absolute value one. You want to make sure that you don't miss that dip on the v. So it's okay if it looks like a line if you're only looking in like this section of the absolute value function, but if you're looking in this section right here of the absolute value function, you want to make sure you don't think it's like that. So make sure that if there is a change in direction anywhere, that you are able to see that on your graph. Okay, so we're going to plug in to absolute value of x first. So if the absolute value of 1 is 1, the absolute value of 0 is 0, and the absolute value of -1 is 1. I feel good about this because I see a change in direction, so I know that this is going to show my v, the point of the v. Now notice here, I've already evaluated the function for +1, but I need to evaluate the function again for +1 because sometimes you're going to have something called a bouncer, where the graph goes from one place and then jumps to another place entirely. So make sure that you always evaluate for every part of the piecewise function for any of the numbers associated with the restrictions in the domain. So let's go ahead and I'm going to highlight our areas again with boxes. So x is less than 1. So for absolute value of x, I'm going to do everything in that blue area. And then for the square root part of the piecewise function, we're going to go from 1 to 5. Okay, and I'm going to show that this one keeps going by putting an arrow. All right, so let's go ahead and do the square root part of the piecewise function. We're going to evaluate for 1, 2, and 5. So if we plug in a 1 for x right here, we'll have 1 minus 1 is 0, 0 plus 1 is 1. If we plug in a 2 right here, we've got 2 minus 1 is 1, the square root of 1 is 1, 1 plus 1 is 2. And then if we plug in a 5 right there, 5 minus 1 is 4, the square root of 4 is 2, 2 plus 1 is 3. Now let's go ahead and plot our points. So we've got the point 1, 1, which is right there. We've got the point 0, 0, which is right there. And we've got the point -1, 1, which is right there. Now because we know generally the shape of an absolute value function, we know that this keeps going on like that. For the second part of the piecewise function, we can plug in again 1, 1. We can plug in the point 2, 2. And we can plug in the point 5, 3. And it does generally match the shape of a square root function. Now, I just made a mistake right here. Notice I put an arrow at the end of that just out of habit, but it doesn't have an arrow. It actually ends, because of the domain restriction, it ends at 5. Okay, the last thing we need to look at are, do we need any open circles anywhere? Well, here's the deal. For x's, for the absolute value part of this piecewise function, the x is not included. So if we were just looking at the red portion, there would be an open circle right there. But then right here, for the square root part of the piecewise function, that point now becomes included. So we don't end up having any sort of jump in our domain or our range because of that. So now let's look at our range. Be really careful on these. A lot of students would go, okay, well, the bottom of the function is where that v is at 0, 0, and then the top of the function is right there, where you're kind of paying attention to endpoints. But then you're leaving out anything in this section right here. So make sure when you do your range, you include everything. So keep in mind here, the range is going to keep going up to infinity, just like the domain went left to infinity. So let's go ahead and write our domain and our range. So domain, we know our highest value is right here, so it corresponds with 5. So we'll have x, and 5 is included, so x is everything less than or equal to 5. And then to the left, it goes on forever. Now, is it okay to say it's less than negative infinity? It's okay to say it, but you don't have to. You can just leave it as x is less than or equal to 5, and then that includes infinity. If we were to write that in interval notation, we do need to include the negative infinity. So you can never equal negative infinity, so we need a parentheses, and then we go all the way to 5, and it includes 5, so we need a bracket. For range, the lowest point, or the lowest y value on our graph, is going to be 0. So we're going to say y. It goes from 0 to positive infinity, or we could say that y is just greater than, because 0 is included. We've got greater than or equal to 0. And now let's do our interval notation. 0 is the smallest number in the range, and it is included, so we need brackets. Positive infinity is the largest number in the range, and it can never be included, so we need parentheses. Okay, let's move on to example 5. So first, let's just pay attention to the different types of functions we're dealing with this piecewise. We've got a line here, we've got a square root function here, and we've got a parabola here. So I'm going to go ahead and highlight our intervals on our graph. So the first interval we have is -5 to -3, which is about right there. And then our second interval is -3 to 0, so about right here. And the third interval is anything greater than 0. Okay. So for our first interval, again, we're dealing with a linear function, or portion of a linear function, so we only need to plug in 2 points to find the shape. Definitely plug in the points that are associated with the restriction. So if I plug in a -5 for x right here, -5 plus 2 is -3, and -3 plus 2 is -1. So now let's go ahead and plot those points. So -5, -3 is going to be right here, and -3, -1 is right here. And I can connect my dots with a line. So the second interval is our square root function. So I'm going to plug in a -3. -3 plus 4 is 1. The square root of 1 is 1. -2 plus 4 is 2. The square root of 2 is about 1.4. And 0 plus 4 is 4. The square root of 4 is 2. So we're going to go ahead. I want you to notice right here, I plugged in -3 twice. That is necessary with piecewise functions, because sometimes on this first example, this just was continuous. It continued where the second portion of the piecewise continued where the first portion left off. But right here, you're going to see a space in the graph where the function jumps from one point to another. So make sure you always evaluate the functions for any of the numbers involved in the restriction, or the domain restriction, even if you have to evaluate it twice. And this is a really good example of where that's very important, because notice where -3 is evaluated for that second interval, the y value is 1 here when the x value was -3. So now we have a point right here. And then at -2, about 1.4, so we're going to have a point about right here, and then at 0 and +2. And it does look like that nice curve of the square root function. All right, so the next part is our parabola section. So we're going to plug in 0, 1, and 2 for that, so we can get a good idea of the shape. So if we plug in 0, 0 squared is 0, 1 squared is 1, and 2 squared is 4. Let's go ahead and plot those points. So at 0, the function, again, notice I'm evaluating it for a different interval, and the function bounces again. So we've got 0, 0, and then 1, 1, and then 2, 4. And because there's no restriction here, like this box doesn't really have an edge to it, it keeps going. So this function will just infinitely get wider and wider and wider as you go. All right, so now let's deal with open circles versus closed, showing numbers that are included or excluded. So the first one is where we're looking at -5. So notice -5 is not included, so we're going to have a hole right there. So we need an open circle at -5. -3, notice -3 is x is less than or equal to -3, so we're going to keep that dot closed. For the second part of the piecewise function, we've got -3 is less than x, so right here we need an open circle. And finally, for that second interval, we've got x is less than 0. So again, we're going to have an open circle right there. Now for the parabola section, x is greater than or equal to 0, so that's going to stay closed. So now we've got the piecewise function showing everything that's included or excluded. So let's now talk about the domain and the range. So it looks like we have a hole right here and right here, but I want you to look. This hole right here is filled in by the lack of a hole in the red portion, and this hole right here is filled in by the point that is included or defined for the parabola section. So if we talk about our domain is going to include everything from -5, not including -5, but everything from -5 all the way to infinity. So we can write that as x is greater than or equal to, or excuse me, x is greater than 5. Or if we were doing interval notation, notice 5 is not included. The largest number in our interval is infinity, so we'll have parentheses around both on the range here. So let's just, I'm going to draw or drag this box over to show our range values. So we're thinking like how high and how low does the graph, or is the graph defined? So we've got a section right there where the graph is defined. So it goes from -3 to -1. -3 is not included, -1 is. So we can say for part of our range, it goes from -3 is less than y, which is less than or equal to -1. That's one section. But now we need to talk about the other section. So we have a gap where we don't have any range values from there to there. Then we do have range values from here, and it keeps on going up to infinity. So even though we've got holes right here and right here, there are corresponding points that fill in the holes on the parabola. So there's holes on the square root function part of the piecewise function, but the holes get filled in by the parabola portion of the piecewise function. So we can say that the range is not only -3 is less than y, which is less than or equal to -1, but it's also where it's that and y is greater than or equal to 0. Now, if we were to do that in interval notation, we've got to have two different intervals. So we've got -3 to -1. -3 is not included, 1 is included. Now, to show that we want both of those sections, we're going to use kind of a wide U to show it's the union of both of these sections. And then the second part is greater than or equal to 0. So we go from 0 is included, to positive infinity, which can never be included. Let's finish up with example 6. So first, let's just look generally at what the shape of the piecewise function is going to be. In the first interval, it's going to be a line. In the second interval, it's going to be a parabola or a part of a parabola. And in the third interval, it's going to be a part of a V. So I know that I'm showing a portion of the graph that's a little weird, but it's probably the best view that you'll get. So let me go ahead and highlight the different portions. So for that first interval, it's going to go from -2 to 0. So let me change my window to show that. Okay, so this is the part where we're going to see a line. And then our next section, our next interval is from 0 to 3. And then finally from 3 to 5. Okay, so let's go ahead and plug in some points. For lines, we only need to plug in 2 points. Make sure you plug in the points associated with the restriction. So 2 times -2, I'm plugging it in right here. 2 times -2 is -4. -4 minus 1 is -5. Then 2 times 0 is 0. 0 minus 1 is -1. So let's go ahead and plot those points. So it goes -2, -5. So that point is right here. 0, -1 is right here. Then let's go on and we can go ahead and connect those 2 points with a line. Now let's do the parabola portion. So I'm going to plug in my numbers into the x right there. So first, 0 minus 1 squared, so -1 squared is 1. 2 minus 1 is 1. 1 squared is 1. Okay, so at this point, I did this when I was preparing for this video. I first started off plugging in 0 and 2, just trying to save time. But as soon as I saw this, what I noticed at that point was that I was going to be missing the vertex of the parabola. And I'll kind of flesh that out for you in just a second. What I knew at that point is I needed to plug in 1 as well. So if I plug in 1, 1 minus 1 is 0, and 0 squared is 0. And then 3 minus 1 is 2, and 2 squared is 4. So first what I'm going to do is I'm going to plot the points if I skipped 1. So I would plug in 0, 1, so that's right here. Then 2, 1, so that's right here. And then 3, 4, which is right here. And if you didn't know what the shape of a parabola or a squared function would be, or an x squared function, you might think that the graph looks like this, or maybe you would do a curve or something like that, but it'd be totally wrong if you don't include the vertex. So be careful and thoughtful about the points you plug in whenever you're graphing. So if we do go ahead and include that 1, 0, we have this, and now we have a nice shape of a parabola that we want. So for the final section, we have an absolute value function, so we know it's going to be a part of a v. Be careful here too, because you don't want to miss the place where the function changes direction. So I'm going to talk about how to kind of tell. So if we plug in a 3 for our x values, I'm plugging now into that third equation, or third function. So 3 plus 3 is 6, and the absolute value of 6 is 6. 4 plus 3 is 7, and the absolute value of 7 is 7. And 5 plus 3 is 8, and the absolute value of 8 is 8. So let's go ahead and plot those points. So we can do 3, 6, which is right here, 4, 7, which is right here, and 5, 8, which is right here. So let me adjust my window a little bit just so it encompasses that. And here's our line. Now here's the deal. If let's just say that the V was right with like this, then what you would have wound up finding is this other, like the point, instead of being right here, it would have been here. So what you would have found in these numbers is that they weren't linear. If at any point the numbers for an absolute value function give you something that's not increasing linearly, then that means you've missed the point of the V. So then you need to plug in some in-between points. Okay, so now let's deal with open circles versus closed circles. So let's look at the beginning of this. It's x is greater than or equal to -2. So that means that this circle needs to be closed because -2 is included as part of the domain. 0, however, for the linear part, 0 is not included. So I'm going to go ahead and make that as an open circle there. Now, for the next part, for the parabola part of the piecewise function, 0 is included. For that, I'll make these really obvious. So 0 is included as part of the domain for the parabola portion of the piecewise function, but 3 is not included. And for that last section, we've got, again, 3 is not included. But 5 is included, so we'll leave it as is. Okay, so this affects our domain. If you notice, even though the 0 is not included here, it is included here, so we don't end up having a gap right here. But here, we do have a gap. So if I were to make this more obvious with my boxes, there's going to be a section where the function is not defined. So I'm going to show it like that. All right, so this affects how we say our domain then. So with our domain, the lowest point in our domain, we're going to have 2 sections here. The lowest point in our domain is the -2. -2 is included, so I'm going to have a less than or equal to. Then x, and then here, because there's a hole right here, you have to say it's less than 3. And we're going to need to do this section now. Again, 3 is the lowest number, but it's not included. So 3 is less than x, which is less than or equal to, and then the largest number in our domain is 5. The way you would write that in interval notation, it's got a little bit of symbolism that's probably new for you. But for this first section, you're going to have -2, 3. You'll have a bracket around -2, a parentheses around 3. And then because we want both of those parts, we're going to make like an uppercase U to show it's the union. It's both of them together. And then you'll have, again, a parentheses for 3, 5, and then a bracket. Now let's talk about the range. So I'm going to go ahead and take off the boxes for the domain. Let's just use this yellow one for the range. So I want you to notice there's a gap from here to here. So we're going to have to show that with our range. Then we have more points, more y values from there to there. And then we have another gap right here. So then we finally have more y values from there to there. So let's just look at what these numbers would be. So for that first section right here, it goes from -5 to -1. So the first part of our range is going to be a -5. Because -5 is included, it's going to be less than or equal to y. Then we're going to go all the way to -1, but -1 is not included, so just y is less than -1. The next section is this right here. Notice this part right here is 0. 0 is included right here, so 0 is less than or equal to y, and then up to 4 right here. So it's less than 4, and then we have a gap. And now we have this section. So we've got now 6. 6 is not included, we've got an open circle right there, so 6 is less than y, but then we have all the way up to 8, and 8 is included, which is less than or equal to 8. And then if we were to do that with interval notation, for this section right here, we'd have bracket -5, comma, -1. -1 is not included, so parentheses. The union of that with bracket, 0 is included, 0, 4, 4 is not. And it's also the union of 6, 6 is not included, so parentheses, comma, 8, 8 is included, so bracket. So there is your final interval notation for the range. All right, so another way you can see kind of where there's these holes in this last example is if you try to evaluate the function for different numbers. So some of these we've already done. If we want to find p of 0, the portion of the piecewise function where 0 is defined for our domain is that second part right here. So what we can do is we can plug in a 0 for x, and 0 minus 1 is -1, -1 squared is 1. So p of 0 is 1. All right, now p of 3. I want you to notice here, for that second interval, 3 is not included. And for the third interval, 3 is also not included. So it's like this is asking what's the value of y when when the x value is 3. And if you notice, there is no value of y because there is no x. There is no value of x. So we would say that this piecewise function is undefined when x is equal to 3. All right, so then if p is -1, well, the interval that includes -1 is 2x minus 1. So 2 times -1 is -2, -1 minus, or -2 minus 1 is -3. Then let's talk about 2. If x is 2, now we're in this interval right here. So we're going to plug in a 2. So 2 plus 3 is 5. The absolute value of 5 is 5. Now, p of 5, again, we're looking for where can we have a 5 in this piecewise function. So it's right here. So 5 plus 3. So p of 5 is 8. And finally, p of 9. Notice the biggest x value you'll see on this piecewise function is 5. So p of 9 does not exist, or in other words, it is undefined. With some side notes. Remember, for piecewise functions, they're all functions. You're never going to have a point where you have more than one point. So keep that in mind. The domain restrictions lead to bouncers. Bouncers are things like this right here, where you have a space in your graph somewhere. And then the last thing to remember is notice the shapes of the graphs. In other words, remember what their parent functions look like, just so you don't miss the shape of the overall piecewise function.